All right, welcome everyone. Welcome to Kubernetes Fortnight. We're doing these every 2 weeks. Today we've got Brian Jimerson from Aspen Mesh, solutions engineer, and we're going to be talking about Istio and Aspen Mesh. So let me go ahead and hand it off to Brian. And if, like I said, if anyone has any questions, just post them in chat, and I should be able to get them asked for you or use the QA system. All right, thank you.
Thanks, Mike. So yeah, like Mike said, my name is Brian Jimerson. I'm a solution engineer with Aspen Mesh, and a lot of people probably haven't heard of Aspen Mesh, but we'll talk about who we are as part of F5. And then today we're going to talk about some of the basics of Istio and what the problems it's trying to solve with customers. So what we're going to talk about today is, really what microservices, how they've come about. I'm sure everybody's heard the term, but what they really are and the challenges that they can present to customers at scale. Introduce Istio as a service mesh and what problems it's trying to solve with microservices. And then we'll look at the installation of Istio, some of the authentication and authorization and encryption that's by default in Istio, some sophisticated traffic management flows that are capable with Istio, and then really observability and visibility of Istio and microservices. And as Mike said, if you have any questions, we can stop and answer them, anytime. So just post them in the Q&A or chat. So first, who's Aspen Mesh? So Aspen Mesh is an incubator at F5. And we were really built to bring enterprise class Istio to the market. So we saw that service mesh was a growing market, and Istio is by far the most adopted service mesh out there. And we wanted to make sure that customers could operate at scale with Istio. So we do have a product that is built on top of Istio to help manage it. At scale, to give you visibility and insight and configuration of multiple Kubernetes clusters in Istio. We also have services and support for Istio for large-scale customers. And we're also a large contributor to the open source Istio project, the upstream Istio project. So we're in the top 5 in terms of contributors for open source Istio as measured by pull requests. So let's start, and I know this is a little basic for everybody, but I think it's important to kind of set the stage to talk about what Istio does and how it does it. So, I think the first thing is kind of looking at the current landscape of the enterprise software development over the last 5, 6, 7 years. And I think most, companies that have been historically brick and mortar and stagnant in terms of software delivery have realized that they need to build software, or use software to deliver, innovation, keep up with their competitors. So engaging with customers and building new products rapidly. And, most large companies that have been around for 100 years, whatever, really didn't have those mechanisms in place. They were building large monoliths that took forever to change. If you needed to update or add a new feature, it could take months to get that feature into production, and they just weren't capable of delivering rapid innovation. And so a large part of that is just the ability, the nature of a monolith. You have multiple teams contributing to the same deployment. You have to have QA schedules and testing. If you made one feature, you had to deploy the whole monolith, and that took forever, and it just wasn't working. And so microservices, although the notion has been around for a long time, has quickly become kind of the de facto development architecture for these companies, because microservices allow individual components to be deployed without really any concern about other features and functions and other microservices. And so really what a microservice is I like Adrian Cockcroft's definition the best. There's some others out there like Martin Fowler, but it's a loosely coupled service-oriented architecture with bounded context. And this allows development teams to move fast, to move individually, and can deliver innovation through software much better than they could before. So I think it's important to kind of unpack this term a little bit, because this sets the stage for what a service mesh and Kubernetes, quite honestly, does. So the first part of this is loosely coupled. What does loosely coupled mean? This is not a new concept in development, but you can generally test to see if it's loosely coupled. If a service has to be updated in concert with all the other services, it's not loosely coupled, meaning you should be able to update one service and deploy it and not have to redeploy all the other services within that system or that application. And the way that coupling happens, that loose coupling, is instead of having a monolith that speaks in memory to different components, you now have to have a protocol and a contract to communicate with other services. And as long as that contract doesn't change, you can independently deploy services without worrying about other services. So, typically those protocols and contracts are HTTP with a REST API, or maybe you're doing asynchronous coupling through a message broker over TCP. But that loose coupling means that you're now doing communication over the network instead of, again, doing it in memory for an application for monolith. The other part of this is bounded context. So the idea with a bounded context is that a service does one thing and one thing very well, and it doesn't concern itself with other parts of the system. And so you have a bounded context if you don't know about your surrounding services. So that means that you don't have to worry about those other services. You just do your one thing and do it very well, and you communicate with them through a contract and a protocol again. So those two kind of terms that are inherent in this definition imply that there's a lot of network communication between services that are participating in the system. Whereas in the monolithic world, again, that was traditionally in memory, maybe some outside calls to an API or database, but for the most part, different libraries and components within a monolith just communicate with each other in memory. So what that really does is it creates this massive growth in network traffic between services. And this graph on the left is kind of a contrived system, but it's not an atypical system. You have 6, 7, 8 microservices. They, again, because of the loose coupling, they all need to communicate with each other over network instead of in memory. And because it's a bounded context, and these services don't necessarily know much about other participating services, there's the potential that any service could have to call another service for some reason. So you have to assume that's going to happen. So you can see just the huge amount of traffic increase over the network as opposed to historical monoliths. Now, this is a very simple 7 microservices is probably a very small application or system. On the right, just for comparison's sake, this is Netflix call graph. Now that's the other extreme. Most organizations are going to be somewhere in the middle, but obviously the complexity you can see in both examples, and you can imagine that most organizations are going to be somewhere in between, but still have a lot of network complexity. So this introduction of all these network calls and communication introduces a lot of new challenges that historically development teams haven't really had to deal with in the past. One of them is the most basic of how do I register my service and what my address is, and how do other services discover my address? How do I route and do load balancing between services? And then in a large system, you have to expect that there's going to be degradation in performance, and there's going to be services that go down, and you have to be able to tolerate that from a calling service through various techniques like timing out and circuit breaker patterns, because you just have to assume that that's the case with that number. How do I see what's going on within my system? How do I view network traffic and latency? How do I view which services are returning errors or slow to respond? How do I aggregate different APIs and different services into a single API? And how do I transform between protocols and data through there? And how do I manage configuration in a highly distributed system? So a lot of these problems, Kubernetes is one of the first what you call a cloud native platform that tried to address some of these, and it's done a really good job on the compute side and the storage side and how to schedule workloads. But it doesn't do much in terms of the traffic between participating services and ingress and egress, and that's kind of a need in the market now that Kubernetes is won the war and everybody's adopting it. There still is a need for handling the network side of things. So that's really where service mesh comes into play, and Istio in particular, but this is really any service mesh, and there are other ones out there outside of Istio. But service meshes and Istio in particular are meant to address a lot of these challenges that are being introduced by these highly distributed, loosely coupled systems. So it tries to offload a lot of these challenges to an infrastructure component, much like Kubernetes did with compute and scheduling. By allowing you to connect and secure microservices, give you sophisticated routing and traffic management, give you visibility into what's going on in the system, and really and applying security. I think one of the important things that Istio and Aspen Mesh and all the different vendors of Istio have realized is that this cloud native world introduces a new way to implement security. The old security controls don't really work in this new world for a number of reasons, but we don't want organizations to take a step back in their security posture. And so, security is first and foremost across the board with Istio. So what does Istio actually look like? It's actually fairly simple from an architectural perspective. Istio has two different components in its simplest form. It has a control plane, which is exactly what it sounds like, much like Kubernetes control plane. There's a component called Istio D, or a pod called Istio D, which does really all of the control functions within the service mesh. And there's data plane, and a data plane is really comprised of running workloads and also what's called a sidecar proxy, which is a container that runs within the same pod as the service. It's actually Envoy, which is a open source project from Lyft, and that comprises the data plane. So any pod that has an Envoy sidecar proxy injected into it is part of the data plane, and Istio D will send information like configuration and certificate rotation and installations and telemetry and things like that. Istio D is responsible for. I think one thing I wanted to point out is Istio D used to be three separate components: Mixer, Pilot, and Citadel. And you still see references to those names. They've all been kind of collapsed into a single Istio D component. But if you see references, you will still see references to, Mixer or Citadel. That's part of Istio D now. They still exist logically, but it's a single component now. So one of the things in the data plane is that Istio does is, and we'll see how it actually does this, but it automatically injects an Envoy proxy into each pod that has one or more microservice containers running within it. And part of that injection is that the Istio D will modify the IP tables for that pod so that all traffic leaving the pod or coming in from external clients to the pod goes to the Envoy proxy, and then Envoy proxy will communicate with the microservice through the loopback interface. So the microservice is never exposed directly to any network interface that can go outside the pod. In this case, it's all Envoy. So how do you get going? How do you install Istio? It's actually remarkably easy to get a default installation of Istio. So in the Istio distribution, which is open source, there's a binary CLI called Istio CTL. And if you run Istio CTL install against a cluster, a Kubernetes cluster, it'll install the control plane. And then you can create a new namespace and label it with Istio injection, or existing namespace with Istio injection. and any workload that, or any pod that gets deployed to that namespace that's labeled will automatically have the sidecar injected, the proxy injected into the pod. So if we kind of tie that back to the original architecture, what happens is when you run the Istio CTL install, that creates a namespace called Istio-system, which is the root namespace for Istio, and it installs Istio-D and related components. It might install an ingress gateway and egress gateway if you want that as well. Some observability tools, but all the control plane stuff will get installed in that Istio system namespace. And then when you create a namespace and label it with Istio injection, there's a mutating webhook that gets fired when a new pod is deployed to the namespace that has that label. And that mutating webhook will start a init container that modifies the IP tables so that the service only listens on the loopback address or loopback interface, and also installs the Envoy proxy. And the IP tables will then route all the traffic to and from that proxy. It's kind of a couple of interesting things here by this approach. One, the service itself, your application, it's really transparent to them. I mean, as long as you're not binding specifically to an interface or IP address, that service never really knows that there's a proxy that's intercepting all the traffic to and from it. The other nice thing about this is that it doesn't really matter what language or your service is written in. It could be Node or Java or Go or whatever. The proxy itself is just communicating via network traffic. So it gives you a lot of flexibility. Your development teams don't really have to do anything special aside from some configuration for routing, and this all just works.
So you're saying too, like when you create something, the webhook's going to add a bunch of the information that Istio needs, and you don't have to change your services or anything like that?
Correct. Absolutely correct. So we'll look at some of the configuration, but there's nothing special your application needs to do. It can reference hosts by the same host name. It can make calls. It's all transparently proxied through the sidecar proxy based on a mutating webhook. And so, back to this example, when you do a kube control apply, whatever your application is, the Istio-D and the mutating webhook are automatically going to grab this pod that gets deployed from this deployment and inject the Envoy proxy and modify the IP tables for that.
So Brian, I see you have Helm installation also available. What's the benefits of Helm versus just using Istio CTL?
Yeah, that's a good question. So Helm is also a way to do it. It's a little more, not unless it's cumbersome, a little more work, obviously, with Helm instead of just using binary. But you also, it's easier to hook into things like CI/CD tools and that sort of thing. It's easier to override configurations. Underneath the hood, they're both calling the same thing. The CTL and Helm are all ultimately doing the same deployment. It's just what your preference is. In practice, most organizations go down the Helm path. They're comfortable with Helm. It's part of their process. But in a sandbox environment, you want to get up and running and kick the tires on Istio. Istio CTL is by far the easiest way to go. Any other questions on kind of the core Istio, what it is, and how to install it? Okay. So one of the things that usually drives people to look at a service mesh like Istio out of the box is peer-to-peer authentication. So if you think back to those call graphs, all the communication that happens between them, that is going over the network, even though it's an internal network. And by default, if you're just running straight up Kubernetes, it's not going to be encrypted. It's not going to be authenticated. It's not going to be authorized, anything of that nature. It's going to be the Wild West. Anything can talk to anything in plain text, and away we go. And that usually flies in the face of most security policies for organizations. So they want encrypted traffic, even if it's internal network, everywhere. They want to know identities, and they want to be able to audit identities of these network calls, and have some level of policy around these. And one of the most common ways to do this is something called mTLS, which stands for mutual TLS. So it's your typical TLS X509 type of protocol, but in mutual TLS, both the client and the server, or the peers, or however you want to upstream, downstream, however you want to call them, they both exchange, they both do the handshake for TLS. So the client will initiate a TLS handshake with the server will in turn do another TLS handshake with client. Within that TLS connection, there is identity based on usually a service account, and also authorization process to make sure that one service can talk to another. So this meets a lot of the requirements for secure communications between services. And the good thing is that Istio does this out of the box. You install it, and it's automatically going to have mTLS communication between pods, unless you override it. So it can do that because of the proxy, and Istio handles the certificate management for you. So it rotates certificates, it revokes certificates, and that sort of thing. And because the running container, the microservice, and the proxy are communicating over the loopback interface, that doesn't really need to be encrypted. So you get mTLS for free out of the box, and this is probably the first thing that everybody looks at. Says I need a service mesh to do mTLS authentication. There's also some confusion sometimes around different types of authentication mechanisms. So mTLS is really peer-to-peer. It's using X509 encryption, and it's really about, hey, is this one pod allowed to talk to this other pod? For authentication and authorization for an end user, whether it's a browser or an external system or something, that doesn't typically use mTLS. One of the things that does work out of the box is using JOT, or JSON Web Tokens. So JOT is part of the OAuth flow, and an end user would authenticate with some identity management system, and that would issue a JOT token that the user would then send as part of the request to an application. And then the sidecar proxy would then authenticate that against that issuer to make sure that the user is allowed to do whatever they're requesting. And then it'll actually propagate that JOT token with requests to other systems as in the header. So JOT is really intended to be for end users to authenticate and be authorized for requests into the system. And again, mTLS is meant to be the auth mechanisms between pods within the system.
Is it terminating at the sidecar, right? Like, so you don't have to do anything with your application to support this, really, or does it go through the sidecar at all? That's what I'm kind of confused.
Yep, it's terminated at the sidecar. So again, the application doesn't need to do anything with encryption or authentication or anything of that nature. It's all terminated from sidecar to sidecar.
Awesome. So like your pod's going to look like it's going to have two containers in it, right? Like the sidecar and then your actual application.
Right. Yeah. So if your pod has one container normally and you deploy it as part of the data plane, it'll have two containers. One being, and it's called Istio proxy, and the other being your application. And again, the IP tables for the pod are modified so that the only communication microservice or the container can have is on the loopback interface, which is attached to Istio proxy as well. And all the other IP addresses are bound to the Istio proxy. So I think to your point, there's nothing really for the application to do. It doesn't need to worry about certificate management, which can be a nightmare. It doesn't need to worry about binding to interfaces or routes or anything like that. It's all handled by the Istio proxy.
Since the
all right.
I'll say since the pod has both of those on the same host, usually they're only communicating like to each other. They're not leaving the host that they're on either, right? Like, so the communication between the Istio proxy and the microservice that's not TLS.
No, that's all just on the loopback.
Yep.
Between the microservice and the Istio proxy. So they're going to be on the same host, the same pod, with the same interfaces, and they're going to communicate on the loopback. And then Istio proxy will transparently proxy requests and responses. If it goes off the node to another node or wherever it might live in Kubernetes, it'll take care of that.
Awesome. Thank you, Ryan.
Yep. Another point here, and I should probably call this out, is that there are different configurations for mTLS. Our recommendation is to enforce mTLS mesh-wide. It's one setting when you install it. And then you can override that to be more permissive if you have, say, legacy workloads that you just won't work, or if you have some need for that, you can override at the individual workload level. But our recommendation is just turn this on, just so you make sure that everything's encrypted and everything's got off on it.
So if you're installing Istio or something like that, you're probably turning on injection for almost all your namespaces, and then you just turn this off for legacy stuff instead of just not including that in an Istio namespace, probably.
Yeah. So by default, the namespaces that you label with this Istio injection equals enabled is going to have, every pod in that namespace is going to have proxy injected into that pod, and which means that it's also going to have mTLS on by default. There are namespaces that you probably wouldn't want to label that, so you don't want it to be part of the data plane. So obviously, like the Kubernetes, the Kube system namespace, and your Istio system namespace, and some other of the system stuff that aren't really running custom workloads, you don't want to label. But the ones that you do label with that Istio injection equals enable will be a participant in data plane, which means you get the proxy, you get mTLS, you get all the Istio goodness. You can override that injection on a per pod basis or per deployment basis through attributes. You can also turn off mTLS and a lot of this other stuff through attributes. So, what we generally recommend is, zero trust, be as secure as possible out of the box. And if you have a specific use case where you need to override that, do it. But that way your developers don't need to worry about, encryption and routing and all that stuff. It's just they're deploying through a CI pipeline, and they automatically get all the Istio goodness out of that. Does that make sense?
That makes sense. Thank you.
So kind of the second step that most people try to leverage, or second set of features that people leverage, is traffic management. So you can do some pretty complex traffic management, as well as controlling ingress and egress into the service mesh. And we'll kind of walk through some of those. So out of the box, there's a lot of stuff that you can do in terms of managing traffic to your workloads that are running in Istio. One of the things I find really cool is weighted routing. Weighted routing, it means having multiple versions of your application deployed side by side and routing a percentage of traffic to each of the versions. And so that's configurable. You can send, let's say you deploy two different versions, you deploy a new version, so you have V1, V2, you could send 75% of your traffic to V1, the old version, and 25% of the traffic to V2 on the inbound part. And so that allows you to do a lot of cool things like canary style deployments. Canary style deployments are just that, where you deploy a new version side by side to the old version. You start to route some percentage of traffic to the new version, and gradually increase that over time while you're testing performance or functions until all the traffic is routed to the new version, and you can retire the old version. It also allows you to do things like A/B testing. So maybe you have a certain group of users that are beta testers or internal users, and you can route traffic to a new version that's running side by side with the old version based on header attributes or other types of attributes. So you can have a group of users testing a new version that you've released, while the rest of the common users are still using the old version until you decide to cut over. So weighted routing does a lot. You can imagine some of the scenarios. Those are two of the basic use cases, but there's a lot of stuff you can do with that. There's locality-based load balancing and failover. So not something I wanted to get into today, but we can talk about it at another point, at some point. But Istio has has a configuration called multi-cluster. And what multi-cluster is you have a logical service mesh instance, a logical Istio instance that spans multiple Kubernetes clusters. And those clusters, maybe you have on-premise Kubernetes cluster and you use a public cloud like EKS as well, or Platform 9. It could span those clusters, or it can span clusters that are in different regions in AWS. As long as there's network connectivity, you can span multiple clusters with a single logical mesh. And so what a lot of people have requirements for is maybe they want to route users to the closest cluster to their location. And you can do that in a multi-cluster configuration with locality-based load balancing, or maybe you have data privacy requirements for different countries, and you want to route users to the country that meets the data privacy requirements for them. And again, another use case for locality-based load balancing. So again, this is kind of an advanced thing, but it's also very useful as people start to mature on Istio. You can also do traffic mirroring. So this is similar to weighted routing. Traffic mirroring means you're sending the difference is mirroring means you're sending 100% of the traffic to two different versions, but only one version is live and the response is sent back to the client. The other version, the response is just kind of sent to nowhere. And this is another useful feature another useful way to do feature testing, where you're sending live traffic to a mirror. The user doesn't know that, but you're sending live traffic to the mirror in conjunction with the live version, and you can do testing of those features. There's also a lot of network resiliency. So, like we talked about before, you have to assume that there's something that's going to go wrong in this large scale. I got hundreds of microservices. They're all talking to each other over a network. There's going to be network issues or performance degradation of a service or something, and you don't want to bring down the whole system because of one of those. So things like a circuit breaker pattern can be done with traffic, and the circuit breaker is where a client can handle a bad response from a server in the mesh and handle it gracefully and not just blow up itself and cause cascading issues. You can set timeouts for requests, and how often you want to retry as well, so you can handle a lot of that degradation. You can also do fault injection. So if you're into this sort of thing and you want to test the resiliency of your applications in the mesh, you can specifically set fault or inject fault into these applications. So you can do things like say, hey, 5% of the requests I want to return a 500 error, and see how the client handles that. Or 10% of the requests I want to inject latency of 100 milliseconds or 1 second, and see how everything handles it. So if you're in a pre-prod environment, you want to test the resiliency of all your applications, you can do fault injection. So a lot of cool stuff you can do. There's obviously more, but those are the ones.
So a lot of these features too are what other projects have built on, like Knative, like scale to zero and requiring like retries until the service is available. So like once you get good with Istio, you can install something like Knative or other stuff on top of it and take advantage of these. It's pretty cool.
Yeah, that's a good point. And a lot of the CD tools that are out there, like Argo and Flux, also use these features to do automated canary deployments and feature testing and things like that as well. So there are a number of projects out there that build upon these features. So just kind of give you this is an all-encompassing here. Oops, sorry. This is an all-encompassing here, but these are the Istio APIs that give you a lot of these traffic management rules. So there's really 4 core ones: virtual service, destination rule, gateway, and service entry. And the virtual service and destination rule are by far the most common. So certainly read the documentation. There's so many settings in the virtual service that you can set. There's no way with that. That's a whole session by itself. But it gets a little confusing as well. So if you are gonna play around with this in a sandbox, the virtual service and destination rule relationship is a little confusing. And honestly, sometimes I wish they'd just combine them because they overlap all the time. But in general, the virtual service configures how a request is routed to a Kubernetes service. within the mesh, and a destination rule at the end of that virtual service then configures how to handle the traffic for that. So I tend to think of virtual service being at the layer 7. And so you can do things like, traffic splitting and weighted routing, and, anything that really kind of deals with layer 7 types of things that virtual service handles. And a destination rule is more at the layer 3, layer 4 level. And so a destination rule, you can apply TLS policies. You can do connection timeouts, things at that layer. But they do kind of go in conjunction with each other. If you usually have one, you usually have the other. But those are the ones that give you all the sophisticated routing and management. There's also a gateway object. We're going to look at ingress and egress gateways in a second here, but a gateway object is what manages an inbound traffic or outbound traffic for an application. So there's an ingress gateway that handles all the inbound traffic, and then you assign a gateway per host or set of hosts that route the traffic into your application.
So Brian, so destination rule would be more services and namespaces, and then gateway would be outside traffic, kind of, or
no,
I'm trying to restrict pod traffic.
Yeah, no, it's more about how to route it and how to route a request, and then what to do with that request before it hits the pod. So if even internally, if you have service A calling service B, you could have a virtual service set up for service B that says, hey, if the URL has /v1, send it to service B's v1 instance. Or if it has /v2 in the URL, send it to v2 of the service B instance. And so that gives you the complex routing within the mesh. The destination rule would then kick in after the virtual service evaluated whatever rules it had, and the destination rule would then say, okay, and I want to make sure all requests are going to terminate TLS at service B, or I want to set a connection timeout, or things at kind of the layer 4 level. So they can handle external requests, but they can also handle internal requests. They're really kind of the core building blocks of traffic management. Does that make sense?
Yeah, that makes sense. So I say,
okay,
over here on the right, like the YAML looks kind of like an ingress resource, but it's not necessarily creating ingress resources behind the scenes, right? Like virtual service is a bit different.
Yeah. So the one on the right is a very simple example, and this is a virtual service that essentially says, okay, any traffic coming from, to your point, an ingress gateway with this host, route to this back end. Front end is the name of the Kubernetes service and the destination. You could do a lot more complex stuff in here. It doesn't necessarily need to be bound to an ingress gateway. It could just be general traffic within the mesh as well. This was just a simple example I had in one of my Git repos that I put in here.
That makes sense.
So you're right. This particular one does handle ingress traffic to a service, but it can also be traffic from another service to the service.
And that's why they created a virtual service instead of just using the ingress resource, right? Probably.
Right. Exactly. That's the challenging part in Istio is there's a lot of different pieces to chain together. But in its simplest form, a virtual service is really wherever the request is coming from, this is how I want it routed to the service that I'm running.
Awesome. Thanks.
And then the other interesting one is a service entry. So there is a setting in Istio that we being Aspen Mesh recommend you turn on. That says it's called outbound traffic policy, and there's a setting for that. One of the values you can set to it is registry only, and what that means is that if an application that's in a mesh tries to call something outside of the mesh, maybe it's a third-party API, or maybe it's a database or something that's not running within the mesh, do not allow it unless it's in the internal service registry for Istio. And so by default, if you set that to registry only, any calls outside of the service mesh that Istio doesn't know about will be rejected. A service entry is a special type of API object that will add an external service by host name to the service registry. So that's how you can control what traffic is, or where egress traffic is allowed to, by turning on the outbound traffic policy to registry only, and then adding service entries for allowed external services. And then all the resilience and testing features that we talked about, these aren't standalone APIs, they're really different configurations within a virtual service or destination rule. But that's also how you configure a lot of these resilience things and testing. I did want to touch on ingress and egress as well. So obviously we've talked a lot about traffic within the mesh, but you're going to have external requests coming in, and you're going to have requests that are going out of the mesh to some sort of external service. And there's a concept of an ingress gateway and egress gateway to handle this. And the ingress gateway actually sits behind your ingress controller on your cluster, and it's an Istio specific object, but it gives you a lot of the routing configuration that you need. So it's another layer configuration, but it's pretty powerful. So one of the things you can do with your ingress gateway and egress gateways, you can configure your mesh to only allow traffic going out through the egress gateway. And if you have dedicated nodes for your ingress and egress gateways, it gives you a lot of capability to do things like audits, or to set firewall rules to only allow traffic from those dedicated node IP addresses. It's definitely a pretty powerful in improving your security posture by having these dedicated gateways for ingress and egress. And to give you an example of what that might look like, so this is a project I was working on before. So we have an application, being the blue box here, that makes a call to a virtual machine outside of the mesh running RabbitMQ. And that call needs to be encrypted over TLS. So through the configuration of egress gateways, virtual service routing, we say that all traffic leaving the mesh needs to be routed through the egress gateway and then out, so that you have visibility into traffic leaving that. The interesting thing about this is that because that connection is encrypted, the application just knows about the host name of the server, the port, the protocol. The communication between the proxy running on that apps pod and the proxy running on the egress gateway is then wrapped and tunneled in mTLS. So it's actually wrapping that encrypted RabbitMQ connection in mTLS between those proxies, and then the proxy on egress gateway will then terminate the mTLS and send on the encrypted traffic to RabbitMQ. So again, another example of the app knows nothing about this proxy. It's just sending it to the host name, and the proxy automatically picks that up and routes it through the gateway. So your developers don't need to know about that.
So this makes this like it's separate. Is the to Brian, a question: is the Istio proxy, is it a pod, or is it a daemon set running on each of the nodes? Does it run on the controller nodes?
No, the Istio proxy is a container that runs. The Istio proxy is a container that runs within the pod.
Okay, so the Istio egress gateway, this isn't separate outside of it?
Yep. So Istio egress gateway, that was good segue. I was going to bring that up. The egress gateway and the ingress gateway are standalone Istio proxies that are configured to handle inbound and outbound traffic. So they're another Envoy proxy that's deployed in Istio's system namespace, and it's a pod running with one container. Or you can scale now, but it's a pod running with just a standalone proxy container.
Okay, that makes sense.
It's a normal deployment. It's not a daemon set or stateful set or anything. It's just a standalone one, and then the configuration again is configured to allow certain ports and traffic through, whether it's inbound or outbound. So,
awesome.
Does that answer your question?
Yeah, that answers it.
Okay. Okay, the last section I wanted to talk about is observability. So again, one of the challenges is you've got all these running microservices making all these network calls, and there's an issue that the end user reports, and you're like, okay, well, I don't even know where to start because there's so much going on here. So, Istio collects a lot of telemetry data from the data plane as well as itself to give you insights into, what's going on in the mesh. So one of the things you can do is just visualize what your mesh looks like. And I want to say here that Istio does collect all this telemetry and it can send it to Prometheus or some sort of data store. The tools I'm showing here are visualization tools, and you can use any tool that you want that supports these protocols. And they're starting to move to open telemetry. So I'm showing you Kiali, but there's other tools out there, commercial and open source, that can give you the same graph visualization based on this data. So it's really the telemetry data that Istio gives you, and you can use your tool of choice. So for example, this is Kiali, and this shows you kind of a call graph for a sample application all the way from the Ingress gateway through services that are running multiple versions of the pods behind them, and all the way, and even out of there. So you can look at things like, you can get data for, are these connections healthy? Are these calls healthy? These are all green arrows in this case, and the blue one's the Mongo because it's TCP. Number of requests, some basic data like that, but it's really good to visualize the whole communication path in a more complex system of microservices. Distributed tracing, this is another big one. So when you do have an issue with a system, it's really hard to tell where that issue is being introduced. If you have 50 microservices that are all calling each other, it's like, okay, well, which one is being slow about this? And so distributed tracing is a very useful tool or way to go about seeing who the culprit is within a call graph. And Istio does this by injecting headers into all the requests for tracing. So things like a correlation ID and a trace ID. It injects that into all the request headers, and then it can send that data to, in this case, this is Jaeger, Zipkin. There's a number of distributed tracing tools out there that can send that data to any of these tools, so that you can visualize, where there's bottlenecks or where there's errors being thrown, and that sort of thing that's causing an issue. And then, just really kind of raw metrics. So again, these metrics are typically stored in Prometheus. You can use your APM tool of choice, whether it's Datadog or Dynatrace, or in this case, this is a Grafana dashboard, but there's a ton of metrics that you can build your dashboards around to look at both the Istio control plane performance and metrics, as well as your applications and those metrics. And you can see in here, it even gives you information about, like, this is mTLS at the bottom there, so you can see that your pods are protected by mTLS in this case, so you can see what's encrypted and what's not, throughput, latency, all sorts of data, and you can pull it into a tool of your choice. So that was about all I had. I did want to kind of, for those who do want to, look at Istio further, here's some quick steps to get something up and running for that you can play around with and look at it. Again, it's open source, so documentation's out there. So, I would recommend, if I were to go about this from the beginning, I would, create some sort of sandbox cluster, whether it's local kind or platform 9, whatever the cluster is. It needs to be Kubernetes. I think it's 119 or above is the minimum version.
We had a question.
Download, install.
We had a question real quick from Eric Adams. Says, does Jaeger take into account mTLS authentication time?
Oh, like to figure out how much overhead there is for TLS? No. So Jaeger is just looking at the communications between the proxies in that case. And then it kind of loses, once it hits the proxy terminates the mTLS, and then there's no real data there. So you can get that data from Envoy and visualize that in something like Grafana. That is a metric that is collected, is for the TLS termination overhead. But Kiali itself doesn't go that deep in there. And we have some pretty good guides around, benchmark performance of Envoy and how to tune Envoy, because obviously there is some overhead with that proxy. But it's what we found is it's, if you tune it properly for your environment, it's fairly minimal.
Perfect. Thank you.
So yeah, so get a sandbox cluster, download and install Istio. They have this concept of profiles when you do the Istio CTL install. I would recommend a demo profile because that kind of installs everything. So it installs the ingress gateway, the egress gateway, core Istio control plane. Install. It doesn't have to be Kelly, Jaeger, and Grafana. Install the tools of your choice. But Kelly, Jaeger, and Grafana are common ones. But if you have other preferences, that's fine. There's a bunch of microservice-based applications to demonstrate a lot of the features in Istio. So book info is actually shipped into Istio distribution. We have one called Catalog Demo, which is a set of microservices as well that you can download and install. And then these are all links, and I'm sure we'll send out the slides. These are all links to different sections of documentation in the Istio website. I think the key ones that everyone wants to get started with are, how do I secure my mesh? How do I get observability in my mesh? And then how do I do this advanced traffic management? So look, there's a lot of good examples in the documentation to be able to do that.
Well, awesome. Thank you so much for your time, Brian. Hope you got.
Yeah, definitely.
Does anyone have any questions or anything? We got pretty close to time. That was a great presentation. I enjoyed it. Thank you. I hope everybody learned something. We'll give a minute for some questions, but I don't know if we're gonna get a whole lot. I don't know if Eric's got another one, but if not, like I said, I'll edit this video and upload it to YouTube in the next couple hours. So if you missed anything, you can check it out there. I guess I'll say thanks for joining us. Do this every 2 weeks. We'll be back in another 2 weeks. Thanks, Brian. Thank you so much.
Thanks, everyone.
Everybody. Yep. Oh, hold on. We published where the benchmarks are. Are you talking about from the presentation?
Oh, yeah. So we used a tool called Fortio, Fortio, which is another open source tool. We're big in open source that does performance testing of Istio in there. So I'll talk to Mike to see how to publish them. They're kind of internal benchmarks, but I can scrub the data. They're for a customer. I can scrub the sensitive stuff and get them out there. But you can run the Fortio tool as well.
I'll see if I can add them into the YouTube comments maybe. And if you have these slides somewhere like GitHub or something, I can add them there. All right, thank you.
I'll get them to you, Mike. All right, thanks everyone.
Thank you. Have a good Thursday.